So essentially what's happening is you're given this statistic. And then last class we had that example that said 5% of TV remotes are found in the freezer or the refrigerator. So that's our null. That's what is believed to be true. But we think that it is more than that. So we're going to try and prove that to be wrong. So we go out and we sample 100 people in the world and we ask them, where is the last place you found your TV remote when you lost it? And we're trying to prove that it's less than 5% or something. So when we calculate our test statistic, what is believed to be true is always in the middle. So this is our null hypothesis. So in this example, it's the point P equals 0.05. That's what's believed to be true. Then we go out and we take a sample, and let's say that 3 out of the 100 people that I sampled told me that they lost their TV remote in the freezer. So that 3% is going to go over here somewhere. This is our sample, 0.03. So when we took our sample, we got 3%. What a test statistic is it is the z-score of our sample. Basically, relative to the 5%, how far away from our z-score is our sample. And our goal is for it to be really far away, because we want our sample to be so different from the population. And we can even add in the example that we talked about with the amount of sleep. So I could change that example where the null hypothesis is that PCA gets 8.4 hours of sleep, but when y'all took a sample, you got 6.25. So we want our sample to be very different than the population, because that's going to help us in proving it wrong. So that's what a test statistic is. It's just a z-score.
Is that considered very different, 6.25?
Well, we don't know. We think it's different, but we're actually going to prove that it's very different. So after you get that test statistic, you're going to calculate from that a p-value. So in the process, it goes your hypotheses, you calculate your test statistic, then you calculate your p-value. All that the p-value is it's the probability, so I want you to write this down, the probability of getting your sample or something more extreme. So I'll let you write that down and then we'll talk about it a little bit more. So what the p-value is, we took our sample, which was the 6.25. So this is our population. This is our sample that we took. It's also the z-score of that is our test statistic. The p-value is the probability of getting this number or something more extreme, meaning something below that, because it's a less than test. So area under the curve, essentially. And how do we find, like in our calculator, how do we find the area under the curve in our calculator? What? Not inverse. Normal CDF. Yeah, so we're going to use normal CDF. We're going to use normal CDF to calculate this, okay? And whatever that area is considered our p-value. So maybe you end up getting 0.03 or something, 3%. So 3% of the time, if I took a sample, I would get this number or something less. Okay, what I want you to do next is you see this link that's under significance level. I want you to write in underneath, before we go to this link, I want you to write in this top bullet point. I'm going to kind of explain what it is. And then we're going to do a little activity that kind of solidifies what a significance level is. So we call significance level alpha. That's the way you'll see it in a problem. And it's always compared to the p-value. So write that next to significance level.
I write in the whole first.
Okay, so the significance level is always chosen before the experiment or study begins. And essentially, what that number represents is it's a chosen percentage that the researcher sets as their limit before the experiment ever begins. That is, if it is above this or below this limit, that's when I'm going to decide to reject the null hypothesis. So if the p-value is less than alpha, we reject. And there's a little phrase. That's the PG version, I guess, but on your paper I wrote. If the p is low, reject the hoe. It's easier to remember. If p-value is greater than alpha, we fail to reject the null hypothesis. So we've got two options. We reject or we fail to reject. Those are our two options. You don't ever accept, remember. Reject or fail to reject. So find your test statistic, calculate the p-value, compare that to alpha. So I want everybody to go to this link, openintro.org, and make sure that you include the backslash and all of that. You can skip the video and go straight to the activity. So what you're going to do is typically, in most experiments that you see, the alpha level is set at 0.05. And essentially what that means is you have a 5% chance of getting your sample. So our sleep example, 8.4, we got 6.25. 5% chance of getting that sample or something more extreme. Or a 5% chance of that happening is what the alpha level is typically set at. And so as you're going through this activity, you're looking at these scatter plots and deciding, does it have an upward trend or is there nothing? It's just a bunch of scattered dots everywhere. So you're going to go through, I think there's like 15 slides, and it's going to say, do you think there's a trend or not? And so at the end of it, it's going to tell you like what percentage you thought had a trend and what percentage didn't. And that's like your significance level. So the more, like the smaller that your number is, the more skeptical you are of believing it to be true. The smaller your alpha is, the more skeptical you are, meaning like you need more proof to believe that something is wrong. If you have a higher alpha level, that means that you are more believable or you accept things to be true. Maybe you're like more naive or something. So go through these slides and we're going to compare what our alpha levels are and see who's the most skeptical and who is more believable, like believes things to be true more often than not. That means like the smaller that your number is means like you need more evidence before you believe something to be true. Okay. The higher your number is like if somebody tells you something, you're gonna believe it.
No.
Like, you don't need much evidence to believe something.
And then apparently you don't know me. I was just clicking random. I was alternating it basically.
0.05 is the average, 5%.
Oh
Yeah.
Because all of them to me never had a.
Yikes.
God.
I got 0.1.
I got 0.02.
So we're all
0.02. So Ben is the most skeptical in here. Does anybody get lower than 0.02?
Gabby got 0.01.
No, she got 0.1.
Oh.
10%.
She got 0.16.
Very skeptical.
I think actually
0.06.
I'm surprised you didn't get it.
I got 0.2. I got exactly.
I'm surprised.
So that was just an activity. This is the significance level will always be given to you if it's not given. So if it's not given, yes, in the problem, then you use alpha equals 0.05 because that is the most average one. If it's not given. Otherwise, it'll say use this significance level or something like that.
I'm pretty extraordinary. That word confuses me. Because extraordinary is very ordinary. Yes, but not like extraordinary.
Okay, the next thing, I didn't have you write any of it because it's a lot.
Thank you.
And we don't really talk a lot about it because we are always going to use the p-value. So we will always calculate the p-value. But the only thing you need to know is kind of what this is. It's called the rejection region approach. And so essentially what you would do, instead of doing test statistic to p-value, you would calculate, so I'm using this 8.4 example. If my rejection region, if my alpha were 0.05, I would want to find the 5th percentile of this normal curve, and that using inverse norm, and I would reject anything, like, so let's say that I did inverse norm of the 5th percentile of this normal curve and I got 6.72. I'm just making that up. Then that means that I would, like with Cameron and Tatum's data, they got 6.25. That would fall in my rejection region, so I'd reject. So it's essentially like finding out your limit before you actually calculate the p-value. It's just another way of doing it. But we always do the p-value. Yeah. It's like going backwards. But they give you the same conclusions. So it's like doing the work before you take the sample. P-value is doing the work after you take the sample. So there's two possible conclusions. We reject the null, or we fail to reject, but we never accept. Okay? So we reject, we fail to reject. The reason why we don't accept is because if you think about, and we kind of talked or touched on this last time, but if you think about like a murder trial or something, the null hypothesis is that this person is believed to be innocent. And then we're going to gather evidence. So this person is innocent. That's the null hypothesis. Then we gather evidence. And we decide one of two outcomes. And what are those outcomes? Guilty or not guilty. So those are the two things that we can prove. But we can't prove innocence, so we can't accept the null hypothesis, but we can prove that it's either wrong or it's not wrong. So that's why we reject or fail to reject. So you're going to go through this calculation process. You're going to come to a decision, and you're going to write the conclusion in context. And I have it written out for you. The only thing I want you to do or add in is circle this HA, the alternative hypothesis, and write that you're going to write these in words. So you're not literally going to say, ha. You're going to put it in context of the problem. And we'll get some practice doing that.
In there?
Yeah. You don't have to write the null hypothesis in context, just the alternative.
We have to memorize.
Yeah.
Since the P.
So this you do need to memorize.
Why do I have to memorize everything? Like, you always have it given to us. Like, the answers to everything.
I don't know. Okay, so here's an example. We're going to state the conclusion if the p-value is 0.0145. So my p-value is given. I'm going to compare it to these alpha levels. So remember that if it's less than alpha, I reject. If it's greater than alpha, then I fail to reject. So 0.0145, is that greater than 0.01 or less? So
Reject.
no.
What?
0.0145 is greater than 0.0100.
No, I thought you were asking the other one.
So I'd fail to reject.
Wait, so wait.
Because 0.0145, my p-value is greater than alpha. In 0.05, my p-value is less than alpha, so I reject.
The next one, do you reject?
What about the last
I
one?
actually really
Yeah, I would reject. You're just comparing the numbers.
P-value,
Yeah,
like,
I go with numbers.
yesterday when we were like talking and we were like, is it far enough away? Is p-value
That's what tells me if it's far enough away or not.
to be considered? Like, oh, okay, this makes
Mhm.
sense.
Yes.
Oh, never mind.
Okay. Okay, next one, example 2. I didn't write this all out.
Shelley did not do a good
It. So this one is asking to draw and shade the curve and calculate the p-value. So this one it's wanting us to calculate the p-value from the test statistic and then state the decision. So for part A, I have a right tail test.
What's that mean?
Tails to the right.
It means it's a greater than.
Oh.
And the test statistic is 1.23. So I'm going to draw my normal curve. My mean is always in the middle. And my test statistic is my z-score. So it's probably going to be somewhere like around here. 1.23. And if it's a right tail test, I want to find the area to the right. Okay? So you told me before that finding area is normal CDF. So if I want to find the area to the right, normal CDF. Nope. My lower bound would be what?
1.23.
My upper bound would be infinity. And since it's a z-score, I use what as my mean and standard deviation? 0 and 1. Good. So somebody tell me what you get. 0.109. Good. Now, this is my p-value. I'm going to take this number and I'm going to compare it to 0.05. Is it greater than or less than?
Greater.
So my p-value is greater than alpha, so I make what decision?
Fail to reject.
Good.
Wait, p-value? What? I thought it'd be
What's
less
alpha?
than.
0.109 is greater than 0.05.
No, 109 is great.
Wait, where's alpha?
It tells me in the problem.
Fail to reject. Oh!
Where?
Part C.
It's hard. Yeah, it is.
Okay, part B.
It is. There we go.
This is a two-tail test, so what would two-tail be? The not equal to.
I don't remember details.
Oh, so
This is
left
very
is less than,
Uh-huh.
right is greater than,
Mhm.
tail is not equal to anything.
And so in my picture, what it's looking like, because my test statistic is negative 2.01, it's going to be over here. But since it's a two-tail, it's going to be the area to the outside here. And I add in positive 2.01, and it's the area to the right here.
Because you're doing both.
Because it's both of them. So it's like the mirror image. So the easiest way to calculate this is taking just one of them and then doubling it. So let's just calculate this and then multiply it times 2. The same thing. And so how would I do that? Normal CDF. Good. To negative 2.01. And then what's my mean and standard deviation? Good. And remember, I'm going to take 2 times that.
So when you get it, you just times 2.
Uh-huh. So what's my final answer?
0.0444.
0.0444.
2 times the normal CDF?
Because it's a two-tail test.
Alright, I'll figure this out later.
Now, is this less than or greater than alpha?
Less than.
So what decision do I make?
Reject.
Reject the hoe. Okay, so here's a whole problem. I just want to write the hypotheses it gives me the p-value, and then I'm going to write the conclusion. So go ahead and take a second to read it. It's talking about college students' average of 7 hours of sleep per night.
Do we use a sample? Standard.
We don't ever use the sample
So I
for our hypotheses. So go back to your 8.1a knowledge.
Don't you use the standard deviation?
Nope.
Use P.
Nope.
We don't need
Use
any
me.
of this.
Yep.
Hypothesis is a statement or claim about property characteristics.
We don't use that.
So for my hypotheses, the null hypothesis would be what?
7.
Not P.
Mu is equal to
Mu equals 7. My alternative, mu is
6.8.
less than.
no less than 7.
What does it say? Oh,
We don't use the sample at all for right now. We'll do that later. Where mu represents what?
Average hour of sleep for college students.
True mean hours of sleep for college students.
Can we do the rest of that after?
We have 5 minutes, don't we?
No, that's
I just want to finish.
The bell for lunch.